But this is the remainder theorem. So from here, and this is basically telling us what the remainder has to look like. Remember, it has to be degree less than the degree of the divisor, or it's got to be 0. The degree of our divisor is x minus a, right? Which is degree 1. So our remainder has to be a constant, basically. It's either going to be identically 0 or some constant. But from this equation, you can actually derive, or from the division algorithm, I should say, you can actually get that the constant is f of a. So you can get the remainder ahead of time, is what I'm saying. I mean, what is the quotient? That's a different story, but you can get the remainder. And so, for instance, here's another example. Here we have this polynomial. This is actually something we saw earlier. And we already saw that the remainder is minus 4. I think we saw that. Let me double check. I think we did. Yep, there it is. See, our remainder, minus 4. But even before doing this division, we could actually get that by just replacing 3 in for x here. And you would get minus 4. It's actually very useful, the remainder theorem. It's good to know it. I mean, we figured out what q of x was by actually dividing. You don't have to divide to get the remainder here, is what I'm saying. We could take this even, and I did give a reason why this is true, as you can see. It's really just what I said already. Because we're dividing by something of degree 1, the remainder is identically 0 or a polynomial of degree 0. Polynomials of degree 0, we know, are non-zero constants. So I'm going to say, okay, well, I'm going to call this constant c. So c is our remainder. So c is just a constant, in other words. We could take this a step further and actually figure out what c is. As I do here, you just replace x by a. I mean, q of a doesn't have to be 0, but that doesn't matter because we get 0 times q of a. So we get the remainder. And that's really what I'm saying. And now that was awesome, but we can actually take this a step further. What if f of a were 0? Well, if f of a is 0, as I have down here, then x minus a is a factor of f, of capital F. So if f of a happens to be 0 here, so this term is gone, then x minus a times something, as I have down here, is f. So again, if f of a is 0, this piece is gone, and we just have this. But this is the same as saying x minus a is a factor of f of x. So we can really determine if something is a factor of f of x. You just evaluate it at x. Excuse me, let me say it again. We can determine if a polynomial has a factor of the form x minus a without actually factoring or doing division. We just replace x by a. And if we get 0, then it's a factor. This is saying that the converse is true. That if x minus a is a factor, then r of x has to be 0, the remainder. So basically, it might be kind of confusing what I'm saying. I hope it's not, but I'm just saying the factor theorem, which is this. So it's really just a very nice consequence of the remainder theorem. But this is telling us that we can figure out factors of a polynomial by just doing this kind of calculation. And that's what I'm doing here. So for instance, in this polynomial, it's not the same as this because we have a minus here. Is x plus 3 a factor of this? Well, if I remember, this is the same as x minus negative 3. The factor would have to be of the form x minus a. So really what you're asking is, from this, if I take this polynomial f and evaluate it at -3, do I get 0? And the answer is yes. So x minus -3, which is x plus 3, is a factor of this. All right, I think we're out of time. All right, so we're actually out of time. So again, yeah, let me